Welcome all to the next class of Fundamentals of Food Process Engineering. So in this class, we will discuss problems related to week 5 syllabus. So we will proceed to the first question. A cross-flow heat exchanger has an area of 60 meters square. The overall heat transfer coefficient is 110 watt per meter square Kelvin. The heat capacity of both the cold and the hot stream is 1100 watt per Kelvin. What is the value of NTU here? So before we proceed, can anyone of you tell me what is a cross-flow heat exchanger? So cross-flow heat exchanger is where both the liquids enter each other at 90 degrees. So essentially both the fluids flow at an angle of 90 degrees, which is why it is known as a cross-flow. So given here is that the area is 60 meters square. The overall heat transfer coefficient is 110 watt per meter square Kelvin. And here the heat capacity is given in the units of watt per Kelvin. So what is the general, what is the difference between a heat capacity and specific heat capacity? You can see that the units are also different. For a specific heat capacity, the value is kilojoule per kg Kelvin, whereas in here the heat capacity unit is given as watt per Kelvin. So any idea what is the difference between specific heat capacity and a normal heat capacity? So a specific heat capacity means that it is the amount of energy required to raise a fluid or a substance temperature by 1 degree Celsius. But when you mean heat capacity, instead of specific you mean just heat capacity, it is nothing but the mass flow rate into specific heat capacity, which is why you have the unit of watt per Kelvin. So what is asked here is NTU. So NTU is actually known as number of transfer units. So this NTU gives a measure of the area or the size of the evaporator. So greater the NTU, you can actually say that greater is the area of or the size of the evaporator. And higher the value of NTU, closer is the heat exchanger reaching its thermodynamic limit. That is, generally it can be seen that higher the NTU, higher the efficiency of the evaporator as well. So NTU is a measure of the area of the evaporator and can also be related to the efficiency of the evaporator. And here U stands for your overall heat transfer coefficient, A stands for the area, and C minimum, it stands for the minimum heat capacity. Like say if you have a cold and hot stream, each having different heat capacities. So for the NTU calculation, you will be using the minimum heat capacity. So in this case, it's the same, which is 1100 watt per Kelvin. And here the heat capacity is actually the product of mass flow rate into specific heat capacity of a fluid. So this is how you will calculate the number of transfer units. So the answer comes out to be 110 into 60 divided by 1100, which is, the answer is 6. So the correct answer to this question is option B. Any question in this? Okay. Moving on to the next question. Surface heat exchangers are also called as A. Direct contact heat exchangers, B. Indirect contact heat exchangers, C. Recuperators, and D. Regenerators. So any clue what could be the answer? So any clue what a surface heat exchanger is? Okay, so surface heat exchangers generally are heat exchangers in which the heat transfer happens via a surface. That surface could be either a flat wall, or it could be a tube, it could be anything. So surface heat exchangers actually transfer heat via a surface. So if you look at the classification of heat exchangers, there are multiple classifications available. This particular classification is based upon the transfer process. The answer is not A actually. So, okay, moving on to the explanation. So, if you classify something according to a transfer process, you have something called as the indirect contact heat exchanger and a direct contact heat exchanger. In an indirect contact heat exchanger, both the fluids do not mix at all. There is no kind of there is no kind of mixture or anything of the two hot and cold fluids. Whereas in case of a direct contact type, you will have a proper mixture, that is both of the liquids mixed together to transfer heat. So what we are interested is in indirect contact type, as I mentioned, because the heat transfer occurs through a particular surface. But indirect contact type is a pretty broad classification. Inside indirect contact itself, there are multiple other types. First is the direct transfer type. Here, direct transfer type means that between your two liquids, there is some direct transfer that is happening. That is, from one liquid, it is transferring to one surface. From that surface, it is immediately transferring to the other liquid. So, in a direct transfer type, what happens is that both the fluids actually enter the heat exchanger simultaneously. So, you will have a specific pipe for a cold fluid, you will have a specific pipe for a hot fluid. And then the heat exchange happens from one pipe to the other. Either it could be through a wall, it could be through a fin, it could be through a pipe, it could be any means. But basically, direct transfer type or recuperators here mean that both the fluids enter the heat exchanger simultaneously, and in that heat exchanger, there is some kind of transfer that is happening. In case of a storage type, what happens is that both the fluids do not enter the heat exchanger simultaneously. What happens is you have one single pipe. In that pipe, first the hot fluid passes through. So from the hot fluid, the heat is transferred to the walls of that pipe. It could be either a matrix or a pipe wall or anything. So first the heat is transferred from the fluid to the pipe. And then once the hot fluid is passed, then the cold fluid is passed through the same pipe again. And when it is passed through the same pipe again, whatever heat was stored inside the pipe will now move on to the cold fluid. So in a surface type storage type evaporators, both the fluids do not flow in simultaneously. Although this is another kind of an indirect contact heat exchanger where both the fluids do not mix, both the fluids do not enter the heat exchanger simultaneously. In case of a fluidized bed, you will have one fluid passing through a pipe. The other fluid will pass through a fluidized bed, and that will transfer the heat. So indirect contact type is actually a broad classification, and surface heat exchanger actually comes under direct transfer type, where your heat exchange happens from one fluid to another simultaneously through a wall or a pipe or anything. So these are known as recuperators. And the storage types are known as regenerators. So any doubt in this? The difference between recuperators and regenerators? So the answer to this question is option C, recuperators. Moving on to third question. LMTD in case of condenser is dashed for a counter and a parallel flow heat exchanger. It will remain the same. It will not be equal. It cannot be determined by just saying it is a counter or a parallel flow, and none of the above. Any clue what is an LMTD? What is the full form of LMTD? Any clue? So LMTD means log mean temperature difference, where this is the formula that is generally given for a counter or a parallel flow. So LMTD is equal to theta 1 minus theta 2 divided by ln theta 1 by theta 2. So we need to understand what theta 1 and theta 2 are here. So let us take a counter and a parallel flow. So what do you mean by a counter flow here? What does generally a counter flow heat exchanger mean? So for no, counter flow need not be exactly for a cooling procedure. So counter flow can be even if you want to heat up a substance also, it doesn't matter. So counter flow is more about the flow arrangement. That is, in a counter flow, one liquid will enter through, let's say from here to here is a heat exchanger. One liquid will enter in this direction, the other liquid will enter in the opposite direction. So you have two oppositely flowing fluids, and that constitutes a counter flow heat exchanger. In case of a parallel flow, both the fluids enter in the same direction. So throughout the heat exchanger, both the fluids will be flowing in the same direction in case of a parallel flow. And in case of a counter flow, both the fluids will be flowing in an opposite direction. Whereas in case of cross flow, as I mentioned in the first question, the fluids will be flowing at a 90-degree angle. So based on the flow arrangement also, you can classify a heat exchanger. So this is how a temperature profile looks for a condenser. So what does a condenser do? It takes in steam and then it condenses it into liquid without changing the temperature of that steam. So basically what it is doing is, it is just taking out the latent heat of vaporization and transferring it to the cold liquid, so that there is only phase change that is happening. There is no temperature change for the hot fluid. There is only a phase change that is happening. So if steam enters at the starting of your heat exchanger, it will go out at the same temperature but as a liquid form. So this is how a parallel heat exchanger looks like. This is the temperature profile of a parallel heat exchanger. Here your x-axis, let us say, is the length of your heat exchanger. So this will say the starting of your heat exchanger, that is at length L equal to 0. And this will be at the end of your heat exchanger where length L is equal to L. So the answer is not B here. So I'll explain you the derivation for this. So in a parallel flow, as you can see here, both the streams are entering in the same direction. Whereas in case of counter flow, one stream is entering in one direction, the other stream is entering through the other direction. So you can see the arrows are different for both of these. Okay. So theta 1 will always be the temperature difference between the two fluids at L equal to 0. And theta 2 will always be the temperature difference at L equal to L, that is here at the end of the heat exchanger. This is valid for all heat exchangers, whether it is counter or parallel, whether it is a condenser or boiler or any normal kind of heat exchanger. This is like the standard terminology for theta 1 and theta 2. So let's say we are taking a parallel heat exchanger where your TH in the inlet and TH in the outlet is the same, but when heat is transferred from the hot to the cold fluid, the temperature of your cold fluid rises. So here you can see at L equal to 0 it is pretty cold, but as you reach the end of the heat exchanger, the temperature rises. So we'll calculate the LMTD for this parallel heat exchanger. So for a parallel flow, your theta 1 is TH minus TC1, okay, and theta 2 is TH minus TC2. So if you substitute these theta 1 and theta 2 in the LMTD equation, you get, let's say LMTD can be termed as TLM here. So TLM is equal to TH minus TC2 minus TH minus TC1 divided by natural log of TH minus TC2 by TH minus TC1. So I'm just substituting theta 1 and theta 2 in this equation. So if you cancel TH, this is the equation that you get for LMTD of a condenser in a parallel flow. So TC1 minus TC2 divided by natural log of TH minus TC2 by TH minus TC1. So we'll keep this in mind. Now we'll derive for the counter flow. So if you see in the counter flow, what your theta 1 is Th minus Tc2. Okay, so whichever is entering first, like say if you are entering, the temperature at which the fluid enters is always 1, and the temperature at which the fluid always leaves the heat exchanger can be considered as 2. So this is Th, this is Tc2, this is Th, this is Tc1, because this is where the cold fluid enters. So theta 1 is Th minus Tc2, theta 2 is Th minus Tc1. Okay, so this is for a counter flow. So what differs between your parallel and your counter flow is just theta 1 and theta 2. If you substitute these back inside the LMTD equation, you get theta 2, that is Th minus Tc1 minus Th minus Tc2 divided by the ln of Th minus Tc1 by Th minus Tc2. Again, if you cancel Th, this is what you get, Tc2 minus Tc1 divided by the ln of this Th minus Tc1 by Th minus Tc2. As you can see here, it's slightly different from your parallel flow. But if you just multiply a minus in the top and the bottom, you get the same LMTD as that of a parallel flow. Is this clear? How we derive theta 1, theta 2? Any doubts in how you find out theta 1, theta 2 and LMTD? Okay, so in case of a condenser or boiler where there is no temperature change in one of the fluids, whether it is a boiler or condenser, there should be no temperature change in one of the fluids. There is only a phase change that is happening. Only in these kinds of heat exchangers, you will have the same LMTD irrespective of the flow arrangement, whether it is counter or parallel. If it was not a condenser or boiler, if it was some normal heat exchanger, your LMTD will not remain the same. In fact, your LMTD of your counter flow will always be greater than the LMTD of your parallel flow. So why are we choosing this LMTD? Any clue why we are even dealing with LMTD in the first place? Why not just Tc2 Th minus Tc? That's what we did in the previous classes and all. We just did hot fluid minus cold fluid, and that was our delta T. Why are we even dealing with LMTD in this case? So we're dealing with LMTD because, as you can see in this temperature profile, your temperature at any length, say L, is not the same as any other length. So your temperature kind of keeps on varying across the heat exchanger, and this variation is actually not even linear. It's kind of a logarithmic variation, which is why we are choosing LMTD to define the delta T here. This LMTD will be a delta T that you will substitute in your Q equal to UA delta T formula. That we will discuss later on in the coming questions. But when you look into a heat exchanger, we are more bothered about LMTD because your temperature keeps on changing with respect to distance in a heat exchanger. This is not in the case of an evaporator. Evaporator, you generally feel that your temperature is constant throughout the evaporator. But in case of a heat exchanger, you will have a temperature variation with length, which is why you are considering LMTD in case of heat exchangers. I hope this is clear. If you guys have any doubt, you can post a question in the chat. So the answer to this question is option A. That is, the LMTD will remain the same only in case of condensers or boilers. So moving on to question 4. Water is heated from 35 degrees Celsius to 75 degrees Celsius by an oil of specific heat of 1.9 kilojoule per kg Kelvin. The fluids are used in a counter flow double pipe heat exchanger, and the oil enters the exchanger at 110 degrees Celsius and leaves at 75 degrees Celsius. Find the log mean temperature difference. So how do you proceed with this? Now that you know what is an LMTD, how do you proceed with this? So the first thing when LMTD is asked, it's always better to first draw a temperature profile based on the kind of flow that is being mentioned here. So this is how a counter flow looks like. Given here, TH1 will always be, 1 will always indicate the temperature at which it is entering, 2 will always indicate the temperature at which it is leaving, any fluid per se. So TH1 is 110 degrees Celsius, which is entering. TH2 is 75 degrees Celsius, that is the temperature at which the hot fluid is leaving. So again, TC1 is 35 degrees Celsius, TC2 75 degrees Celsius. So if you look at a temperature profile for a counter flow, first you need to draw a temperature profile in order to understand and calculate the LMTD. So your hot fluid will enter from one direction, that is from 110 degrees Celsius, it will go all the way to 75 degrees Celsius. Whereas in case of a cold fluid, it will enter the opposite direction. It will enter from 35 degrees Celsius and it will go all the way up till 75 degrees Celsius. So how do you calculate LMTD for this? What is theta 1 and theta 2 in this case? Anybody is calculating theta 1 and theta 2? Okay, so theta 1 is the temperature difference at always the starting L equal to 0, and theta 2 will always be L equal to L, that is the final length. So theta 1 minus theta 2 divided by ln theta 1 by theta 2. So yeah, theta 1 is TH1 minus TC2. In this case, it is 110 minus 75 degrees Celsius, which is 35 degrees Celsius. Theta 2 will be this region, 75 minus 35, which is 40 degrees Celsius. So now if you substitute these values inside this formula, what do you get? Your log mean temperature difference. Okay, so if you substitute these values in LMTD equation, you will get theta 2 minus theta 1 divided by ln of theta 2 by theta 1. So 40 minus 35 divided by ln of 40 by 35, which will give you 37.44 degrees Celsius. So your answer to this question is option B. Any clue? Do you need me to go slow? You can let me know. Any doubt? Yeah, so the answer is 37.44. So moving on to question 5. I hope you understand how to draw a temperature profile of a counter flow and a parallel flow. So this will be important in identifying the LMTD, or else it will get a bit difficult. So moving on to question 5. In a co-current heat exchanger, orange juice is heated from 8 degrees Celsius to 76 degrees Celsius by hot water, which changes its temperature from 110 to 80 degrees Celsius. So in this case, find the log mean temperature difference. So here, another synonym for a parallel heat exchanger is co-current heat exchanger. So you have co-current and counter-current. So in this case, how would you calculate your LMTD? So again, you can draw a temperature profile. So for a parallel flow, both your fluids will enter from the same direction. So hot fluid is entering from 110 at 110 degrees Celsius and reducing to 80 degrees Celsius. Your cold fluid is entering in the same direction from 8 degrees Celsius. Its temperature is rising to 76 degrees Celsius. So what is the theta 1 and theta 2 in this case? Okay, theta 1 is 102 and theta 2 is 4. Yeah. So Again, if you calculate theta 1, it will be temperature difference at the starting 110 minus 8 degrees Celsius, which is 102, and theta 2 will be 80 minus 76, which is 4 degrees Celsius. So what is the LMTD? So what is the value of LMTD that you are getting when you substitute these two values? So you get 4 minus 102 divided by ln of 4 by 102, which is 30.26 degrees Celsius. So your answer to this question is option A. Yeah, so it's coming 30.26. Yeah. So can you notice any very stark difference between the temperature profile of a parallel flow and a counter flow? So in the previous slide we discussed a counter flow, and here we are discussing a parallel flow. What is the very major, apart from the flow direction, what is the major difference that you see in a parallel and a counter flow? More than the increase in the end temperatures, there is something that is very starkly different if you compare this parallel and a counter flow. It's even visible in your okay, yeah. So if you look at this and if you look at this, you will see a very major difference in the delta T here. So if you look at the entire length of your counter flow, you see that your delta T remains pretty much same at the start and the end of your heat exchanger. I mean, there is a difference, that is 35 degrees and 40 degrees, but the difference is pretty minute. But here, in case of a parallel flow, just look at the difference. At the first, it is somewhere around 102 degrees Celsius, but towards the end of the heat exchanger, it is basically only 4 degrees Celsius. So what happens when your delta T reduces? What happens to heat transfer?
Increases.
When your delta T reduces, what happens to heat transfer? Delta T is your driving force. So if delta T decreases, your heat transfer will also decrease. Q is equal to UA into delta T. So if delta T decreases, your Q will also decrease. So what will happen in a parallel flow is, initially you have a very good delta T. So you will have a very good heat transfer. But by the time it reaches the end of the heat exchanger, there is very less delta T here. So your heat exchange becomes much more difficult as it goes to the end of the heat exchanger. Whereas in case of a counter flow, if you see, the delta T is pretty much maintained constant, almost constant rather. It's pretty much same from the start and the end. So your heat exchange happens throughout the heat exchanger. Whereas in case of a parallel flow, majority of your heat exchange will happen initially, but towards the end, since the delta T is it's very much small, there will barely be any heat exchange. So this is the major difference between a counter flow and a parallel flow. Your delta T difference with length will drastically change in case of a parallel flow, whereas in case of a counter flow, it will remain pretty much constant. So moving on to the next question. The fouling factor of a heat exchanger is found to be 0.00014 meters per Kelvin per watt. The overall heat transfer coefficient of a clean heat exchanger is 1600 watt per meters per Kelvin. So calculate the overall heat transfer coefficient of a dirty heat exchanger. So what do you mean by a fouling factor here? So when do you consider a fouling factor? What do you decipher from the name fouling here. So when you repeatedly use a heat exchanger, what will happen is you will have a lot of, since it's getting heated and everything, you will have a lot of dust particles, ash, soot, any kind of, uh, yeah, exactly. So there'll be a lot of scale formation that is happening because some things are getting deposited on the walls or the tubes or the shell side or anything. So because of this deposition that is happening, there'll be something called a scale formation that will reduce the heat transfer. So because of this scale formation or a fouling that is happening inside a heat exchanger, the amount of heat that can be transferred will automatically reduce. So the overall heat transfer coefficient of a clean heat exchanger and a dirty heat exchanger will not be the same. So you need to consider this fouling factor in order to accurately determine what is the heat transfer coefficient and hence what is the heat transfer in a dirty heat exchanger. So this happens over time when things start depositing on the heat exchanger. So how do you calculate what is the relation between a fouling factor and a overall heat transfer coefficient is your fouling factor, which is RF, is equal to 1 by U dirty minus 1 by U clean. That is the resistance caused by a dirty heat exchanger minus the resistance caused by a clean heat exchanger will give you how much is the fouling factor or how much is the resistance caused due to the fouling factor. So in this case, what do you find out as your U dirty if you substitute the values? You have RF given here as 0.00014 meter square Kelvin per watt, and your U clean, that is the heat transfer coefficient of a clean heat exchanger, is given as 1600. So over time when it becomes dirty, so what will be the U dirty in this case? So U dirty, when you rearrange this, yeah, you will get a value of 1307.19, which is correct. Yeah, option is D. Any doubt in what a fouling factor means? Okay, so moving on to the next question. Statement 1. In a cross flow, the hot and cold fluid flow in the heat exchanger in opposite directions. And in a mixed cross flow in a surface evaporator, the hot and cold fluid mix with each other for heat transfer. So which one of these statements are true and which one of these are false? Okay, any other answer for statement 1? What are the three types of flow that we studied? One, we studied parallel, the second we studied counter, the third we studied cross. So how is the flow arrangement in a cross flow? Yeah, so first one is actually false. There's a difference between counter and cross. Counter is opposite directions, cross is 90 degrees. So your hot and cold fluid will flow at 90 degrees in the heat exchanger. So statement 1 is false. What about statement 2? In a mixed cross flow in a surface evaporator, the hot and cold fluid mix with each other. There is actually a hint in the statement. It is a surface evaporator. So will the fluids mix or not? Yeah, so in a surface evaporator, the fluids will not mix. So what do you mean by mixed cross flow here? So there are two kinds of cross flow here. One is called as an unmixed cross flow. The second is known as a mixed cross flow. In unmixed cross flow, here you can see, let's say one of the fluids come through these small pipes. The other fluid flows through these plates that separate uh, the pipes. So you will have each between these two plates you will have the other fluid passing through. So between these two plates there is no mixture. That is, even uh, your both the fluids go unmixed. One fluid will go separately in tubes, like in the pink region here. The other fluid will pass through separately between the plates. Whereas in case of mixed cross flow, there are no plates. Basically, your one fluid will just randomly enter your heat exchanger, whereas the other fluid will pass through tubes. So this mixed cross flow is used to make so the mixed cross flow is used to maintain a specific a uniform temperature throughout the heat exchanger. I'm not sure of the industrial example yet. I have to get back to you. But these are the two kinds of I mean, there are mixed and unmixed is based on one single fluid. The two fluids do not mix. It is whether the mixing of the same fluid throughout the heat exchanger or not is the question here. So in a mixed cross flow, there are no plates to separate the fluids. Whereas in case of an unmixed cross flow, the plates are separated and the fluid will enter between the two plates. So here statement 2 is false. I'll get back to you regarding the industrial examples. So the answer to this question is option C. In fact, your cross flow, this can happen in a shell and tube heat exchanger also. Anything that passes through a shell and tube will have a mixture of co-current, counter-current as well as a cross flow. So I'll get back to the more specific examples in case of a cross flow. So moving on to question 8. A heat exchanger having an area of 64 meters square and an overall heat transfer coefficient of 750 watt per meter square Kelvin uses a counter current type of flow. The temperature of the cold fluid changes from 10 to 55 degrees Celsius, whereas that of the hot fluid changes from 100 to 55 degrees Celsius. So find the heat supply to the system. So how do you proceed with this? When you get temperatures of the inlet and the outlet feed, the first thing you do is you will calculate the LMTD. So can anyone tell me how the temperature profile looks like and what is the theta 1 and theta 2? It's a counter current type. So this is how a counter flow will look like. Your hot fluid will go from 100 to, sorry, yeah, there's a small mistake here. So this is 55 degrees Celsius and your cold fluid will go from 10 to 55 degrees Celsius in the opposite direction. So what is theta 1 and theta 2 in this case? This is actually 55. So what is your theta 1 and theta 2 coming out to be? Yeah, so for theta 1 and theta 2, both it is coming out to be 45 degrees. So in this case, how will you do calculate LMTD? When both your theta 1 and your theta 2 turns out to be the same, if you substitute it in LMTD formula, it will give you 0. But that is not the case here. There is heat transfer that is happening. There is some delta T, there is some driving force. So what do you do in this case? So when you have theta 1 and theta 2 to be the same, instead of calculating LMTD, which will turn out to be 0, we consider your delta T as your theta 1 or your theta 2. That is, delta T will be equal to theta 1 equal to theta 2. So with that, you can calculate the heat transfer. You will not go for LMTD when your theta 1 and theta 2 turns out to be the same. So you will have Q equal to UA into delta T in this case. So U is 750 watt per meter square Kelvin. Area is found to be 64 meters square, and your delta T or theta that you calculated is 45 degrees. So Q turns out to be 2160 kilowatt. If you didn't have theta 1 and theta 2 to be equal, then you will calculate your LMTD, and that LMTD you will substitute as theta here. Only when your theta 1 and theta 2 are the same will you just directly consider it, or else anytime you deal with the heat exchanger, your theta will always be LMTD theta, not the normal delta T. So that you need to keep in mind. So the answer to this question is option D. Any doubt so far? Okay. So moving on to question 9. In which of the following kind of heat exchanger the heat transfer occurs by mixing of the fluid? So there are 4 types. All of these are specific heat exchangers. Steam injection heat exchanger, shell and tube heat exchanger, plate heat exchanger, and double tube heat exchanger. So what is the answer to this question? The heat transfer occurs by mixing of the fluid. So the moment you say mixing of the fluids, yeah, the answer is A. The moment you say mixing of the fluids, it's a kind of a direct contact type of heat exchanger. So in a shell and tube, you will have one fluid passing in a shell. There will be like a huge shell. It's literally like a shell, and you will have multiple tubes inside the shell. So you will have one fluid in the shell side and one fluid in the tube side. So in a shell and tube heat exchanger, there is no mixing of the fluids. Both your plate heat exchanger and double tube heat exchanger are also a kind of a surface heat exchangers. So in your plate heat exchanger, both the fluids will be separated by a wall or a plate. In case of a double tube heat exchanger, you will have concentric tubes where the inner tube will have one fluid, say the cold fluid, and the outer tube will have the hot fluid. So again, in this case also, you will not have any mixing of the fluids. So all these 3 types are indirect contact heat exchanger, whereas steam injection is a direct contact heat exchanger, where what will happen is you will have your cold fluid or a cold feed that is passed through one direction, and you will have a very high pressure steam that is supplied directly into the feed, and this will result in mixing of the fluids and hence the heat transfer as well. So steam injection or steam infusion is a kind of a heat exchanger where you will have heat transfer occurring by mixing of the fluids. So the answer to this question is option A. Moving on to the last question. The capacity ratio of a heat exchanger was found to be 1. If the efficiency of a counterflow heat exchanger was found to be 0.8, calculate the number of transfer units. So let's go one by one. So what is the capacity ratio of a heat exchanger? What do you mean by capacity? In the first place, we discussed it in the first question. We discussed what is the capacity of a fluid in terms of a different unit instead of kilojoule per kg Kelvin. So a capacity ratio is the ratio of products of mass flow rate into specific heat capacity. So capacity is the product of mass flow rate and specific heat capacity. The moment you say capacity ratio, you will divide that of the cold fluid by the hot fluid. So the ratio of the capacity of the cold fluid divided by the capacity of the hot fluid will give you the capacity ratio. So let us assume, so when is R equal to 1? So from this formula, when can you make out that R is equal to 1? So when you're dealing with same cold and fluid, if the nature of the cold fluid and the hot fluid is the same, let's say you're dealing with water in both the cases. So if you're dealing with water in both the cases, your specific heat capacity will be pretty much the same. And if you are letting the two fluids enter at the same mass flow rate inside the heat exchanger, then your mass flow rate will also be the same. So when you are dealing with the same liquid at the same mass flow rate, your capacity ratio will be 1 for that particular heat exchanger. So if the hot and the cold fluid are the same and enters the heat exchanger at the same flow rate, R can be considered as 1. So when R is equal to 1, the efficiency of a counterflow heat exchanger can be given by number of transfer units divided by 1 plus number of transfer units. The derivation of which is given in the last, I think the last lecture of your week, the last lesson of your week. So your efficiency will be different. So in case of a parallel flow heat exchanger, your efficiency will be different. In case of a counterflow heat exchanger, your efficiency will be different. So based on what the R value is, your efficiency and your relation between efficiency and NTU will also change. So in this case, what are you getting as the number of transfer units as? If you substitute the values, yeah. So when you substitute the values, you get NTU equal to 4. So the answer to this question is option C. So any doubts in the lecture so far? Any doubts in the problems? How to calculate the LMTD? How to draw a temperature profile? And what is the relationship between Q and your LMTD? Q between your heat flux. So all these questions, all these basic questions are there in your assignments, and hopefully these questions will help you understand how to solve these questions as well. So if you have any doubts, you can post it in the chat, or else we'll end the class.